ne répond pas. Donc, je crois que je me suis là. It's like it's in Zurich or
It's outside.
and it's like a spin-off.
No.
It's research. It's not a company. And it's areas transport or human factors, everything. Aren't they closing down daytime? I thought originally you were an engineer. Okay, you're mechanical engineer. Fine. That's been for quite a while. Okay, and what's your position? I realize, and you have it. You guys are preparing this transition.
Good morning. Good morning, everybody. Dear guest, dear colleague. We have today a very, a lot of presentation. That's why we need to start. And first of all, thank you very much that you arrived. Thank you very much, because for us, the guest is the main important person in our institute. It's our heart with our guest. And I want to start this conference with some special welcome from our new guide, our new students, and my colleague will help me.
It's with great pleasure that I open this the 19th International Multi-Conference on Liability in Statistics and Transportation and Communication. I am delighted to welcome so many of you to the Transport and Telecommunication Institute. I wish you all a very fruitful work to welcome so many of you and nice meetings. Have a good time, and thank you very much.
Excuse me, it's the only first-year students, first-year bachelor program robotics. That's why, so short presentation. Okay, let me introduce myself. I'm vice rector of our institute and chairwoman of our institute. And for me, I think very, very important and exciting event open our conference. Today we have 19th International Multi-Conference, and I hope next year we need, I think, twice more auditorium because we will have a special conference. Yes, and first of all, I want to give the floor to the director of our institute, Ms. Kanos, for welcome.
Thank you, Professor Jacek. Good morning, dear friends, dear participants, dear colleagues. My situation now is much easier because now already announced practically half of my speech, which I have prepared. but I can only join him in welcoming you here in Riga, and we have two categories here in our audience. We have good friends and persons who has come here for several years already, who are regular participants of our international scientific gathering, and we are very, very thankful to them and happy that they have decided to accept our institute and our conference as a place for sharing of their knowledge and their thoughts and their new ideas. But also we have second category, newcomers, the persons who are here maybe for the first time. And I can inform you that this year we have participants, registered participants to the conference from 18 countries. And we have received a record high number of abstracts for the participation in the conference. Of course, not everybody who has sent abstract will be present today or tomorrow and will make his presentation in person, but nevertheless, as I said, 18 countries, and particularly we are proud that there are some more and more participants from Western European countries, and we have not only participants but keynote speakers, and we will hear them very soon, from France, from UK, from Germany, also from remote countries like Japan, the United States, India, and others. But we welcome you all here, not only from the states which I mentioned. Also, this year we have at least 2 new sections during our conference. It's transport and energy and the data science in transportation, which we hope will allow you better and to a bigger extent to share your research results and your scientific ideas. Also, we have this year the parallel session with the Coast Action project related to the tendencies of future mobility development. And we also, participants of this session are here in this audience, and we are welcoming them too. That means we are very proud that our conference every year is becoming stronger and more professional. Next year we will celebrate 20th anniversary, and as Professor Yatsky said, we will do our best to organize it as a real event and milestone in not only in the development of our institute, but in the science and research development of at least of this country. Just in few words, I can inform you that this year we already are used to organization of several big events, and very important events, because in May we celebrated here 100th anniversary since creation of our predecessor in Riga Institute of Civil Aviation Engineers, which has happened in 1990 in another country, in another city, in Kiev, and during 100 years it has changed its name and changed the places, but it was very big event. Even this institute has ceased to exist more than 20 years ago, but more than 5,000 people from all over the world has had its graduates, and they came together in order to remember the institute, in order to remember Riga and Latvia, and to celebrate this very important event. Also in September we celebrated 20th anniversary since creation of this present institute, Transport and Telecommunication Institute. As we said, next year we are going to continue this row of celebrations. Just in 2 words about how we spent our last year here at TCI. I will not speak about number of students and the number of professors, but we have been quite successful in implementation of 2 European Union funded projects. First is more infrastructure related. It's for modernization of so-called STEM programs. You know all what STEM means. And we have created electronic library. We have created a center of robotics. we have done other infrastructure developments using this project. But in parallel, we have also some so-called soft project from European Union Social Fund for the increasing of quality and administrative capacity of teaching staff. And this project allows us to invite 12 professors from abroad for lecturing here in our institute. We are using quite actively, and already some people has been here from different countries, and even more will come. Also, one of the activities of this project is to invite doctoral students from outside. Also, this allows us, for our teachers, to receive internships in businesses, in business companies in Latvia. That means our institute not only celebrating different important events, but working and improving, and in both directions, if I can say, in infrastructure development, in human capital development, and we hope that we will continue the same way, in the same manner, also not only until next year, until 20th conference, but more years to come. And then I would like to wish you all the best, interesting days here, good presentations, new thoughts, new partnerships, and we will love to see you all here next year and many years afterwards. Thank you very much for your coming.
Our rector did that we organize this conference each year, and we think that it's very important in our strategy to develop modern University of Applied Science. And why we organize this conference each year? Because we know the knowledge is the new gold, and it's a possibility to share this knowledge between us and collaborate, because networking and collaborating is one of the important platforms for research today. And of course, it's not only collaboration between research institutes and academic entities, it's also with business, with community, with government, and we are happy that we have also in this auditorium representative of our main partner in business, for example, Riga Airport, Riga Coach Terminal, and other important for us entities. And main topic for this conference, of course, about modern technology, how we use this modern technology, and especially for society, for improvement quality of life. Because, of course, if we speak about connected and automated transport, if we speak about integrated traffic networks, smart cities, something like this, it's all time for quality of our life. And our tradition session increase as usual, because the name of our conference, Reliability and Statistics, and we usually have two classic sessions. One is applied statistics, the second one is reliability. We call it this year Data Science in Transportation. And of course we have our traditional session about smart city, about sustainable transport development, and we add also session transport in energy. Today we have very active postdoc which work in this area. Then, as usual, because we are first institute in Latvia who opened 20 years before the first program in logistics. So we have the topic smart solution for supply chain management, and we have our traditional topic intelligent transport system, and of course our heart usual with aviation. So we continue our applied research in aviation. Third, it's our session for this conference. But today it's impossible to do something with technology without good management, without good education in this aspect. So our traditional session in the conference also about innovative economic and wider impact of technology, and about education and training in this in engineering. And as you know, maybe from the program, that this year we have a special guest. We can say that it's a project and big theme of this project is very, very exciting topic. It's about how automated and connected vehicle influence on the community in wider terms. And this is cost action 1622 WISE ACT. And the key question, I think, for this, it's automated, it's good or not. And we have our plenary speakers also about it. I want to present them. First, our speaker, and I'm very happy that 7 years before, he was first time in our institute also as plenary speaker, is Professor Konstantinos Antonios. He is the Chief of Transportation Research Department in Munich and also leader, I think, the project Cost Action and leader of many projects. I know that he has a lot of PhD and I'm very happy that he will present so, good topic for our country also, because mobility and sustainable urban mobility and smart solutions is very important for Latvia, for Riga, and our representative of municipality here in this auditorium. I think they will be happy your presentation. But when we speak about automated connected vehicle, of course it's about infrastructure also, and we prepare for it. And we are happy that our next speaker from our country, lovely country, Latvia, is a young researcher, but I think he is very advanced already. It's from our partner institute, Electronic and Computer Science Research Institute, Kasper Ozels, and he will present a short automated and connected driving in Latvia. But we know that it's impossible without artificial intelligence, because it's very close research area for this technology implementation. So we need artificial intelligence, especially for 4th and 5th level of automated vehicle. And our next speaker from France, plenary speaker, Professor Eric Garcia, and he is the director of Artificial Intelligence Institute in Grenoble, professor in computer science, and he also will have a very interesting topic for researcher for auditorium. And this year we have 2 plenary speakers from France, and our next speaker from France about also very important things, sensors, how we use the data from sensors. And this is Professor Dr. Fabien Montet, and his topic about how to use georeference programs and other things. And as I told you before, it's without education and training in our world, and all things change and change also education in this area. And I'm very happy that in our cost action we also discuss this. And I present the speaker for tomorrow. We have special tutorial for tomorrow, special plenary speaker from our cost action. Professor Dr. Bernd van Beer. Yesterday I told him that I usually recommend my students the papers from him about how to do state of the art in the literature, state of the art in some research topic. And Professor will have tutorial about education tomorrow at 9 o'clock, and I invite you all. And of course, we also want to show you a little our institute. And it will be organized 3 special tours around our labs today twice. You can see that today one time. You can see the time in the coffee break, second coffee break. It's 4 p.m. And then tomorrow you can join for 2 special tours at 10 o'clock after tutorial, and at 1 o'clock it's during the lunch. Yes, I think maybe it will be interesting for next collaboration in some research area. And of course we are happy that our partner institute also will present today the self-driving car developed in Latvia. Yes, it will be in the time after the lunch. Please enjoy and welcome in our Transport and Telecommunication Institute. Our first plenary speaker.
So I'll try to do it from my computer. It's not a big deal, just some videos will be a little bit nicer, maybe for you, less worry. In the meantime, I would like to thank you very much, Professor Inagiatsky, indeed. I was here 7 years ago, and it was my first time in the League of the Baltic countries, and I was really impressed, and I was really looking forward to a new opportunity to come, and thank you for giving it to me, to all of us actually. I would like to first of all clarify that the chair and later of the cost actions, Nicolas Tomopoulos, just a working group leader. And in the next 35 minutes, I'm going to discuss a little bit some things about the future of mobility. So mobility, we are in a very, very interesting place right now. And this is exhibited by the fact that everybody wants to work in mobility, which is great, welcome, and let's all work together and learn from you. But we don't really know what it's going to be, how it's going to be in the future. These are very, very many unknowns. And unfortunately, I'm not going to answer your questions now. Maybe I will create more questions, and I think that's good. Yeah. So first of all, I'm going to start with the internal debate. What is going on in my mind? And I'm not really sure what is going to happen. That's why I cannot really say that. But I'm going to try to present my thought process and try to say, okay, what are the two options, how it's going to happen. And then talk a little bit about shared automated vehicles, urban air mobility, which is another field that we're working a lot and has a lot of similarities, a lot of differences. And at the end, some reflections to try to summarize all these and see how we can start thinking maybe about the future. So there are several scenarios, okay? So first of all, are we moving into a rapid development and explosion of new things, or are we looking at the stagnation and things business as usual? And this is what we have been promised, not us, our parents or grandparents actually. And really what we got is this. So, we have to think about what we want to do. So the problem with predictions is always that it's very difficult to make predictions, especially about the future, okay? So we always have 2020 ideas about the past and how we, or especially others, could have done things better. But when we're trying to forecast, it's very hard. And the reason is that there are many, many, many uncertainties. So now I'm using 2050 as an arbitrary time plan for the future. And there are extremely many, many things that could change, and we cannot forecast, we cannot foresee. And these are external to us. So even if we assume we are the best transportation engineers or whatever in the world, we cannot forecast, the population changes and many other exogenous things. By the way, this is also good because it also gives us an excuse because we can say, our model, our thought process was perfect, but then, the people who gave us the GDP projections or the other external things were wrong. So that's good. Okay. And this is the part of the internal debate. So we saw these things about flying cars and everything and so on. And by the way, I speak a lot about flying cars, and I've been working a lot of this in the last few years. I'm one of the biggest skeptics, and I think that's healthy. It's healthy to have people working on the field who are not drinking the Kool-Aid only, but are also thinking, okay, will it work, will it not work, and so on. It doesn't mean it has to be only these people, but okay. So here what I'm trying to do, again, taking 2050 as the timeline, as the horizon, and saying today we're 2020, okay, in a couple of months. It helps a little with the math. So 30 years ago, car of the year was the Citroën XM. And we're lucky because that specific car, is Citroën, more futuristic, whatever, of its time. But if you look at this and cars today, nothing really has changed. Somebody could argue that they don't build them as they used to or whatever, but in general, all the main characteristics are the same. Maybe a little bit of a gadgets more, a nav screen, or Bluetooth to play music or whatever, but the way the car operates, it hasn't changed. Somebody could take it a little bit further and say 60 years ago, car of the year was Chevrolet Corvair. Still, all the main principles were pretty much unchanged. Even 100 years ago, if we really want to push it, The Model T, okay, of course it's not the same, and probably we could not even drive it if there was one in front of us today, but all the same principles, all the same concepts have remained constant. On the other hand, again, I'm opening my mind now, okay? On the other hand, 10 years ago, if somebody asked you, how many rides will Uber do in 2019, what would your response be? What is Uber? Okay, because Uber was just created, incorporated as a company called Uber Cab in March 2019, so 10.5 years ago. And nowadays, it's making 15 million trips per day. And it has started, arguably, a change in the way that mobility works. Okay, so many of you probably used Bolt yesterday, others maybe, these shared scooters or whatever. What is the problem now? That the problem is that this is not sustainable. This doesn't make sense. This is only possible because there are some nice people who are willing to pay us to spend tens of billions per year so that we can drive Uber and Bolt and these scooters and these shared bikes at these prices. And why are they doing it? They're doing it because, as the Uber CFO said a couple of years ago, when autonomous vehicles come, it will be like printing money. Until then, it is like burning money. And the problem is, personal opinion, that they can only burn money, they only have enough money until the shareholders realize that makes sense for a few years. What is the expected time that automated vehicles, intentionally I'm trying to avoid the word autonomous, right? We're shifting away from that, I guess, but anyway. What automated vehicles, and by automated at level 5 is, when are they going to come? Well, Tesla said last year, BMW says last year or 2 years ago, and so on. You have built your own, etc. That's not what I'm talking about. Waymo is doing thousands of trips per day with driverless cars, or not driverless, with attendants and so on in the US already. That's not the point. The point is to take a car from here and go to Greece, or to, I don't know, Beijing or whatever, without a driver in it, level 5. Nowadays, most people say, or many people, researchers, and I'm not talking about random people, very serious people that many of us know, Steven Sladover from Calpa, for example, that this is going to happen between 2075 and never. And now, even more people are starting to agree and get on that boat. And again, I'm not talking about a Navia shuttle moving around in a predefined route at 12 kilometers per hour. This we have, and it's wonderful, it's great, we're working on that. I'm talking about the general case we discussed before. Okay, some other things. Again, the point that we don't know what is going to happen. In the last few years, we've seen some also very interesting things, not only in terms of development, but also in terms of politics, we didn't expect. We don't know what to expect. The other side, so far I had the pessimistic view. The optimistic view is that all new technologies happen very, 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 very rapidly. So people would say, yeah, 100 years ago cars started increasing much more slowly, but then cell phones much faster, and so on. So that's true. Technology is flying, it's going on very quickly. Another criticism that people shoot down, it's very expensive. I mean, it doesn't make sense to have flying cars, okay? Already they're on the ground and they're expensive. To keep them on the air, it's more expensive. It's physics, makes sense. But even that, and I'm subscribing to that, but I agree that I might be too much of a rectangular square engineer who looks at things rationally and does not recognize the fact that, all the prices drop, so maybe tomorrow there's a fantastic new battery that is very cheap and you don't need to charge. You charge in 2 minutes and you have 1 week's worth of flying around and so on. So I'm open to that. That's why I'm saying internal debate. I don't know, okay? I honestly don't have the answer for this. And then we have things like autonomy, which is maybe one of the biggest unicorns in the area of autonomous vehicles. And I'm going to talk about shared autonomous vehicles a little bit here, because if we just have an autonomous vehicle and we replace our car that we drive with another one, an autonomous, it's not a big deal, right? I mean, it doesn't change things a lot. Maybe I will be able to, you know, read a book or something while driving, or do some work or whatever. At the end of the day, it will not change a lot. Shared autonomous vehicles, for automated sleep, are what will change the world. But this is also extremely complicated. There are many, many impacts. I don't expect you to read any of this. That's the point. The point is that you cannot read it, okay? But I have a very good PhD student who is working with that and creating this kind of octopuses, or octopi, whatever is the word, okay? Where we're trying to see the impacts and the contributions potential of certain autonomous vehicles and the factors that might affect their success. And we see that there is a lot of work on that, okay? A lot of work already. So we start with a meta-analysis and we see the results. These are all people who are like very well-established colleagues and they have spent a lot of effort with very smart PhDs and postdocs and themselves very smart, etc. And they publish results, of course, on somewhat different conditions and so on. This is the impact of these kind of services, future predicted, on the vehicle kilometers traveled. And we see that this ranges from a reduction of 18 or 35% to an increase of 90%. So this is a very wide range, okay? And we have to understand why, what are the parameters. But we don't know. Maybe we switch a little bit, we change the way we think about something, we change the parameters, we change the scenarios, and we get very wildly different results. Maybe this is the range that we will experience, but for different segments, for different aspects. But we have to really understand this better, because when we want to, I mean, the research that we do, it's fine. We want to publish papers, get promoted, get tenure, etc., get more projects, but at the end of the day, as Professor Yatsky said, I mean, the important point is to drive policy and have some real impact in the world, evidence-driven policy. I'm going to close with that. But if a politician asks us and we say, yeah, it might be between a 30% reduction and a 90% increase of the vehicle kilometers traveled, I think they will go to somebody else. Similarly, vehicle replacement of such services. Okay, we all know the famous Lisbon study. Each vehicle replaces 10, but there is also a very big range and also some much smaller numbers that we need to consider. Expected penetration rate of shared autonomous vehicle services. Forget the fact that we don't expect this to be available until 2070. We now look at the range of researchers and we see that there is a very big range. Okay? Different parameters, different kinds of aspects that might have properties of the service, and so on. And why does this happen? It happens because we're trying to forecast how people are going to use them, but there are so many reasons, there are so many factors that we need to consider, and they're all uncertain. So we don't have uncertainty squared or cubed, we have uncertainty or reliability of very high degrees that interact in unpredictable ways. And then we move a little bit to urban air mobility. So if we think that being on the ground is that hard, how it's going to be if we start flying around? Okay? And I'm sure all of you have seen and you know the parameters of urban air mobility. Until now, it's receiving a lot of push from both big heavyweights in the industry like Airbus or Boeing, but also from startups. And like I said, I'm very skeptical, but being one of the advantages of being located in Munich is that Airbus is nearby, so we have had a lot of interactions with them. And, you know, even if I don't believe it so much, why not, you know, work with some students, do some research? It's certainly an interesting topic. So one of the things that we're trying to consider is how we can model this. And the problem here is that we have no idea how this is going to work. So here I'm not going to give you answers again. I'm just going to show you some of the different ways that this can be handled, some of the different configurations that we can have. So we have one configuration. Anyway, that's my solution. one configuration that's a direct network. By the way, this is the direct network that I don't really like using at all, but all my students, they say, oh, I started here, I did my first iteration, the student false network. It's like, please, can you do something else? So after that, it's Munich, but from this only, it is, so, I mean, you can see, am I able to fly from one vertiport to the other? One thing for whoever is maybe not fully aware of that, this flying car will not take off from our driveway or from our balcony or from the street in front. It will fly from vertiports that will cost between 10 and 100 million euros to build, blah, 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 blah. So it's not very, that's another complication. But the point is that can I fly like from one point to the other, or will it be organized in a hub and spoke fashion, so to speak? This is the direct way, okay? So here I can fly direct to my destination, or I can go through some other hubs and we meet some other people. The problem here is what? As we will see later, some simulation results. Oh, these flying taxis go 150 kilometers per hour, 250 kilometers per hour. So this is going to be very, very fast. Yes, but like I said, it's not going to be right in front of here. Maybe at best it will be at the top of the building. So in a few minutes to go to the elevator, I need a few minutes to go there, a few minutes to get processed, because okay, it's not an air Baltic flight, but it's also not my car. So there is something in between that's going to take me a few minutes. Already I've lost 15 minutes if I'm in the building. Another 15 minutes at the end. So now, immediately, the benefits that I get at the speed are not very, very big. And this is, okay. And there's the point of how am I going to route these things. So am I going to the closest area, to the closest vertiport to me, or am I going to the one that is going to give me the fastest overall time? And how am I deciding this? Now we go to the nicer images. So this is the greater metropolitan region of Munich. Okay, so Munich is 1.3 million, but it's also kind of so this is a big part of Bavaria, and we're using this as our playground. First, until now only in our computers, but maybe that will change. We're doing the feasibility study for Upper Bavaria, okay, for urban air mobility. And surprisingly, in Germany, in Bavaria, Upper Bavaria is the lower part. It was really confusing me a lot. It took me a couple of years to realize why Upper Bavaria is down and Lower Bavaria is up. Anybody have an idea? No, well, yes, indirectly it is from the elevation actually, okay, because the Alps is higher in the south and lower in the north. So at some point I figured it out and that was good. So we have now this area, and the reason why we have this area is when we sat down and started placing vertiports, possible vertiports, we talk with the airport, we talk with the big companies, we talk with the city and so on, we started seeing that it's not to go from the airport to the downtown. You have a connection with the train, it's not ideal we complain, but when we put it down and calculate, that makes sense. So we made some assumptions and we came up with, first of all, this situation. So this situation tells us that if we have a quote-unquote slow urban air mobility, so flying speeds of 150 kilometers per hour, and a 20-minute processing time, which as I mentioned before, is not unrealistic, okay? It sounds a lot, but if you start adding it up, considering that in a city like Munich, you might have 10 vertiports in one of the current scenarios that we're thinking. And the fast scenario, which says 250 kilometers flight time and 7 minutes processing time. So this could be maybe frequent flyers or people with a fast track, like at the airport, that they go very fast. The important thing here is that we see what the travel times are to cover other areas, so an accessibility using urban air mobility. But this is not very interesting. What is more interesting is if we compare it with a better faster way to access some points in currently car, public transport, taxi, whatever. So we compare with the best way, and we see that in a slow urban mobility scenario on the left, essentially it's never faster than the existing services. Okay? So there is a legend there, and the white is 0 to 10 minutes gain, the light orange 0 to 10 minutes lost, the heavier red is up to more than 20 minutes of loss, and so on. And only the blue, the dark blue, is 40 minutes of gain. And you see, in the slow urban mobility case, it doesn't make any sense. In the fast urban mobility, for the majority of the city and the highly populated areas, it does make sense. In some of the other areas that are not very well served with existing mobility options, it's getting a little bit better. The problem, of course, is that these are very sparsely populated areas, so now your business model suffers. By the way, I was really surprised at the beginning. Airbus was saying, if this is not public transport, we don't care. But now I think they realize that that's not realistic. So, and actually, even Uber. So Uber, in the Uber Elevate 2017 conference, I think they said, oh, we're going to have fully electric this and that networks, and they showed their vertiports, etc. And at the end, when they start their Uber flights, they are regular helicopters, with a pilot, and so on. Which is fine, it's great, but it's not public transport. It's for a few people to go from Newark or LaGuardia or whatever, the airports, to the top of the helipads at the top of their buildings. Okay. So another problem, another situation is right now we assume that we can fly wherever we want, okay? But this is not going to happen. So we know that people are complaining. I mean, in Munich, for example, they're not allowed to build a third runway because of noise restrictions. So how is it going to be with big mosquitoes flying over us and landing not, 10 kilometers away, landing in the vertical right on the top of the building or a little bit in the next building? It's not going to work very easily like that. So if we start, so this is a direct option. But then if we start looking at restrictions and we say, okay, we are not allowed to fly over residential areas, then if we just remove some inhabited areas and so on, we are removing these areas. So already it might look good, but now you have removed all of Munich, essentially. So you have to go to the suburbs to take this. It's not very good. And this is essentially how it looks in the center area. So if you start restricting residential, we start with everything is allowed, everything goes, okay? But no. If you are not allowed to fly over cities, over residential areas, you have 89% available. But then if you're not allowed to be within half a kilometer, already, you only have a small amount. If you're not allowed to fly within 1 kilometer, not allowed to fly within 2 kilometers. And these are not crazy scenarios that we are building. These are close to what people are recommending. And I'm not saying no, right? Because it's not only noise, it's also safety. So I did some research with a student of mine on trying to understand the attitudes and perceptions of people towards these things, how many would use it, who would use it, under what conditions, and so on. And we made some scenarios, and one of the things that I really wanted to really very carefully push is safety. So we paid a lot of attention to tell them, this is going to be as safe as a car, 2 times safer, 2 times more dangerous, and all these are reasonable, yeah. And at the end of the day, this didn't play any role in the models, nothing. So it's like, no, this doesn't make sense. So I told the full student, okay, please try to look at more of the data. We had also some flow text that they analyzed. So the point was that no matter what we tell people, they believe if it's flying, it's going to be as safe as commercial airlines. And they don't even think that they understand that, okay, they ignore the fact that we told them it's as safe as a car, 2 times safer, 2 times more dangerous, but they also said that it costs as much as a taxi. It costs as much as Uber. How can it be? I mean, I think all of us here understand that. Anyway, so these are for me the main issues, that if the prices are competitive with cars and Uber or whatever, they're going to be falling off the sky. There's no other way. You can make them 100% safe, but then they will cost a lot. Okay, and now we go one step further and say, okay, fine. I mean, I cannot, there's nothing left for me to use. So what can I do? Okay, maybe I can argue that I will go use so-called infrastructure-based flight. So we fly over the motorways, over the train lines, over the tram lines, and so on. And this gives us very, very restrictive options, of course, as you can guess. Anyway, there are a lot of questions, okay, that we have here, obviously. I hope at least I'm giving you some of the range and some of the things we have to think about. So the question is not when will a Volocopter or City Airbus or Mariana or Lilu be able to fly for half an hour. The question is when will we be able to solve all these things. And I will say later, technology was never the problem. With advanced driver assistance systems 20 years ago, the reason the things were hitting our heads against the wall were not related to technology and if the LiDAR or the whatever sensor or the radar works. The problem was who pays if there is a crash. Is it the vehicle manufacturer, the system integrator, the sensor integrator, the sensor developer, the driver, and so on? These are the problems we'll have to fight. Okay, and now try to summarize it, try to think about this. So, Hollywood always has these dystopic movies, always the bad things happen. If you look into the future, I mean, I like science fiction, and I haven't seen a pleasant one, right? Maybe one for kids, but most of them do not seem to be a place we want to live. But this has been forever, right? Metropolis was in the 1920s. The hope is that, humans, we are very good at managing. I mean, we're pushing it a little bit more always, and we are getting closer to the brink, but still, so far we have managed. And this is maybe the danger. This is maybe what will get us more off the thing. But in any case, what can we do to look into the future? I mean, presumably, US President Lyndon B. Johnson said, ranges are for cattle, give me a number. I'm talking here to experts in reliability and statistics, and you all understand that 42 is never the answer. Okay? When I say that to my students, nobody reacts, but here there are also some people who are more experienced and respond, and that's good. And it's getting actually worse. When I was saying that to my students 15 years ago, some people reacted now. Anyway, so 42 is never the answer. 42 plus or minus 5, perhaps. And also, if we say, what is going to be the answer? What's going to be the percentage of certain autonomous vehicles or urban air mobility in 10 years? If I say 32%, I'm certainly wrong. Okay, we understand that. If I give a range, maybe I have some chances of not being wrong. Then the problem is, of course, that it's many, many people who ask us about precise predictions. And the danger is that if we tell the politician, the policymaker, whatever, no, I cannot give you the prediction, what's going to happen? For an hour. They're going to go to the next guy who will happily just go like, help me. So, we have to fight with this, keep our integrity, be careful, try to educate, that's very important, to educate people, and also, try to improve our forecasts, of course, and be more convincing. This is a figure I like very much. By the way, the work group, I'm mostly involved in this cost action, this scenario analysis, and this has also made me look at some more formal books, and I think that was one of the books suggested by to try to read more formally about scenario development and evaluation. So now we have, we are from today and we're going to the future. What happens as we go further into the future? First of all, predeterminants, things we know, start to decrease. There are fewer things we know, okay, if we go to the future, clearly. And uncertainties increase as we go into the future. So now we have 3 ranges, this F, S, and H. So F is okay, I can forecast 5 years into the future, maybe 10, and so on, how much are things going to change. I'm not going to make that comment, but how much things can change. Then, very far into the future, I can only hope for the best. I mean, what can I tell about 2050? Plus, I would not care, but But in between, we can build scenarios. In between, we can try to think what could happen. And it's not necessarily, interdisciplinarity is very important because we are good at some things, but we are bad at other things. We are good at everything. I can speak about myself, okay? I'm very good with numbers, with equations. I spare you equations today because you know that's not the point. But there are other people who have other visions, other ideas, other inputs, and it's very good to work together and develop these scenarios. Another figure is the last figure from this book, or red book, is events, is this pyramid. So we start and say, okay, we see some events, some things that happen, and we try to do something based on these. But the point is that under these, there are patterns that generate these events. And we have to try to understand the patterns. But beyond the patterns, there are many, 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 many other things. There's the structure of things that we need to try to understand. And this is, again, you're not supposed to read this, but this was part of the brainstorming we did in the previous meeting, I think, in Bratislava. We did working through 5 of post-action. And I started thinking, okay, we'll have 5 bullets, and it was organized, it was, I don't remember which part of the board, but later we got many great ideas, which was wonderful, but then we said, okay, what are we going to do now? We're like, oops. But yeah. So what I'm going to do, sensitivity analysis. Sensitivity analysis is a tool I really think is very important. It was actually already defined into the previous post-action multitude that brought us here 7 years ago, and we've been using it a lot. So these here are 4 scenarios. You don't need to know what these scenarios are, and this represents 65,000 simulation runs. But I think you get the point, and I think it's a very eloquent point that hopefully even a non-engineer might appreciate. The problem I have is that sometimes even, not statisticians, but people that should understand, tell me, but why choose scenario 4? We're assuming lower is better. Okay? Why choose scenario 4 when there are instances of scenario 4 that are worse than scenario 2 and 3, or even 1? At that point, I give up. But anyway, you get the point. So I said before, technology is not the limiting factor. Okay? So we know all these things, we know the trolley dilemma very well right now. Companies are very fast to give answers. So another famous one that I really enjoyed was when a few years ago somebody asked, okay, what will autonomous vehicles do? Will they prioritize the safety of the passengers, of pedestrians, or whatever? There was this question that if they prioritize pedestrians, then it's going to be a huge game. Oh, no, wait, let's go jump in front of it and see when it starts. So Mercedes the next day said, my driver, my passenger is my customer, I'm protecting my customer, fair enough. Last slide. A lot of questions, right? I mean, I didn't answer anything. I literally opened my mind. I literally said what I'm thinking, and I'm trying to figure out myself, and I hope I get some feedback from you. Which modes will be available when, and which role will they have? I mean, I honestly tried very hard to not talk about these scooters, but I failed because I'm talking about them now. I don't think, obviously, that they're making a lot of sense. Not to try for yourself and have it around, but as a model, okay? They cost 2/3 of Drive Now in June. At least. There's one goal. And there are a lot of questions about how are we going to deploy them? How are we going to use them? How are we going to pay for them? And who is going to do that? And we see it's very interesting to observe how they develop. So I think last Christmas, I go to in Greece, they just show up everywhere on every sidewalk, nobody knew anything about RelStat. In Germany, last year, at the end of the year, people were telling me, oh, we know that the regulation will be passed beginning of April, and let's be ready, and let's do things, and maybe do a pilot before, and so on. April 4th, regulation passed, okay, and then everybody was listening. Before that day, not a single scooter was seen anywhere now. Okay, from that, I'd like to thank you.
Please, your question.
Co-chair, sorry.
Thanks so much, Costas. You are so passionate. I have a question. Yesterday, I received an email by a person I know in Torino that is very against automated vehicles. And his theory is studied a lot and regularly send me some interesting, how to say, or press or something else, or some outcome from research. And the last one was quite interesting because it seems odd to me because it's something I'm thinking about, but I want to share this aspect with you. Saying that in several studies, now I don't remember but I can check who is the author, some university in the US, these researchers find out in a survey or something, so in I don't know what, that people are much more confident towards robots than human beings in disclosing very private and personal stuff, any kind of sentiment or feeling, or because they think that effectively they are, how to say, sort of no soul, mute, and something that you can't tell anything because they will not disclose to anyone. But we know perfectly that behind people that can get a lot of information. So what about in your studies, I've seen simulation and so on. I'm wondering about a sort of, probably what we want to do in the construction, how do people effectively really perceive these kind of vehicles, because a lot of survey has been done so far using SP and so on, about the perception of people, but effectively, what about the confidence in terms of disclosing of my data? Because it seems that the most part of people is feeling safe and secure about that, but this is not true. So, which will be, according to you, the political reaction about that? They will be, how to say, quiet, not saying, not disclosing that because it's more convenient for the business side. Don't say to people, hey, wake up, the situation is different or not, because this is the interesting sliding door.
I mean, people are very much aware of these, the privacy implications of these automated vehicles, because people will know where you are at any given time, right? My argument is, personally, the way I see it, they already know because of my smartphone. So I think many people, the majority, will be willing to take the comfort, the convenience of something like that if it is available at the end of the day. Right? But that's my personal view. We are asking people a lot and we get all sorts of extreme responses. It also matters a lot in which area, in which country and so on. It also matters a lot which segment of the population. Because older people, for example, or younger people who cannot drive, who do not have an alternative, this mobility improvement will be great for them. But for others who have an alternative, there is a lot of attitude. So what surprises me a lot when we talk about autonomous vehicles, quite often people say, oh my God, are you going to take my car from me? I like driving. It's like, what are you talking about? I hate driving. But no, they see, you know, these Alfa Romeo commercials or the BMW, Freudian Fahren and so on, which maybe 10 to the -6 of the time we spend driving. But that's what people think. They think it's freedom, they think whatever. We have to figure out. We have a lot of work.
This means effectively that this should shorten or could shorten the time for the implementation. But as you show, a lot of this stuff is absurd or quite crazy because it will not improve our life. So my fear is that effectively the misperception of people could create terrific or terrible scenarios in the future. And that will be probably too late. In some of the first slides you show effectively what's happened from the idea in the 50s and before about the autonomous or flying cars and now the congestion in the roads. So this happened. This could happen again in a worse way. So I think that our responsibility is to probably open the eyes of people or make the perception correct and so change this misperception in a real perception.
It's naive when we're dealing with people who say that because of the automated vehicles, traffic will reduce. Nowadays, I think pretty much everybody, there's enough evidence to show that it's not going to happen. We know that. We know this from decades ago. But now I think pretty much everybody understands. Nobody thinks that with automated vehicles or self-autonomous vehicles, because vehicles with one vehicle to replace 10 now will have, you know, empty streets during peak periods or whatever.
And this could be also different among the countries, because I suppose that in Italy, for example, quite recent last year, A survey made by Quattro Ruote is a journal, a specific journal for cars, it's four-wheel. Show that the Italian, the most part of the Italian are against effectively the automated vehicles. Why? For several reasons. Also the pleasure of driving and so on. So this happens in our country, probably in Greece and the Southern Europe could be similar. In the US, I don't think so. So this is another, how to say, variable to take into consideration. The cultural difference could play a role.
Which is good because it's also much easier to implement it in the US and much harder to do it in Italy and Greece. So it goes together with reality.
Thank you so much.
Professor, I have a question about your simulation results on urban air mobility. Yes, I was watching your presentation quite carefully, and I only see one, to my mind, important word on one slide. It's safety. Of course, it's prediction, as you said, yeah, but still, I'm practically convinced that making such simulations, such prediction, and such a detailed and careful one, you paid more attention to this issue as well as you presented here. Your view, your vision, how such air mobility, urban air mobility, traffic can be organized, yes, because it's never, in any way, it will be more dangerous as it is now, because now cars are facing problems with accidents, with crashes, but if they will fly, there will be more danger to fall down and so on. We know in aviation it's strict rules, it's system of air traffic controllers and so on. How your prediction is how this traffic could be organized in order not to create complete chaos and full of tragedies?
Fully with you. I am, as I said, very skeptical about this thing, and safety is going to be a very big issue, one of the biggest issues here. The only safe system, this applies to cars, applies to everything, is no movement. Okay? The only way to have vision zero, not the only, but the convenient way to have vision zero is no cars and no flying cars. For us, we are interacting with the experts, we are developing the traffic control. So I'm not an expert in air traffic control, and I'm not developing this system. We are fortunate in the sense that we are working very closely with big players, and like the Airbus and the Eurocontrol and so on, who give us the input of the scenarios, we evaluate them and give them back. So it is certainly a very big aspect, and there is a lot of people working with us. Nowadays, research has to be very interdisciplinary. And we're working very closely in getting impact from all these people, evaluating and giving them feedback on how to look at the network.
We have one more question, the last one.
Thank you very much. Thank you for your presentation, Professor, and giving us an insight into your thinking. Now, you said yourself that you have a certain position within the industrial partners. You have an insight with Airbus and perhaps being in Munich, the car makers as well. And you spoke at the same time about your scenario of shared automated vehicles. Now, how do you evaluate the car maker's position towards this trade-off between selling more cars and implementing this vision of shared automated vehicles? And what tip would you give to policymakers in this study?
I'm talking a lot, especially with BMW, that has a very big, clear investment on sharing fleets with Drive Now and everything. They don't answer to a satisfactory way. My current thinking is that this is an experiment for them. They're losing money, clearly, in Drive Now and these kind of things. The one tangible benefit that I've seen over and over again, and I try to check with them, and they smile in a way that implies maybe is that it's not a way to go from A to B. It's a way for people to cheaply, with 10 euros, do a test drive of the latest Mini, the latest BMW X2, the latest Cabrio, BMW or whatever, and get hooked and buy a BMW. So in this sense, it's just a marketing tool. Other than that, they try everything. So my office is close to one of their facilities, and every week almost, there is a new mobility service by BMW. So at some point for 3 weeks, there was a van parked in front of my office, said, I don't remember, Alphabet Mobility Service by BMW. There was a guy playing with his tablet all day, never moved. I guess this pilot failed. And then, something else will come. They have now, I have supervised a student who was building on an app that they have mostly for internal consumption, but partly they also have to the world. I think it's called URBY, U-R-B-Y, that they want to try to integrate all these services to go to the airport with public transport, etc. Why? Because they want to be able to convince you that drive now is better, or driving your car is better. I mean, I don't have a very clear understanding. We still understand.
Okay, thank you very much, Professor. One present for you, and maybe I want to show you this book about Latvia, and it was made basic using drone, so it's especially the topic of thought.
Thank you very much.
I give the floor our next speaker, Dr. Kaspars Ozols from Electronic and Computer Science Research Institute.
Okay, good morning everyone. First I would like to say huge thank you to the host and organizers for welcoming me here and giving this opportunity to speak with you and speak about automated and connected driving in Latvia. Before I go into details, I just wanted to represent who I am. So my name is Kaspars Ozols. I work as a Deputy Director of Development as well as Senior Researcher at EDI, where I'm leading different teams of engineers and scientists. I graduated at Riga Technical University a few years ago, where I got my PhD in asynchronous data acquisition for non-statical signals. And currently, my expertise is aligned with the development of smart, embedded, and cooperative systems. So, yeah, I have participated in 9 European level projects, starting from Framework 7 for Artemis projects, and ending up with the Horizon 2020 projects, Aeronet projects, and also I'm involved in post-action, which is great. In those projects, I do modeling, simulation, system and different device development, integration, validation and testing in different areas: smart health, smart mobility, smart manufacturing, and yes, one of those topics is smart mobility, which I'm talking right now. I have supervised several students in engineering students, bachelor students, master thesis, and recently also got an award from Latvian Science Academy for one of the best or significant scientific achievements in Latvia, which I will present later on in my presentation. About EDI, so where are we coming from? So EDI is a research center located in Riga, Latvia, and it's specializing in the development of smart embedded cooperative systems. By smart, we mean we create algorithms, methods, different kinds of solutions. In one word, we create intelligence. By embedded, we mean that we are embedding this intelligence in different kinds of embedded systems, whether these systems are based on processors, microprocessors, GPUs, FPGAs, systems on chips, and so on. And by cooperative, we mean communication technologies. So those systems can communicate with each other. So the systems can communicate with the infrastructure, as well with the cloud and so on. And by systems, we mean that we are developing everything starting from the hardware up to the software and also application level. And all this comes to different application areas. These are smart health, smart mobility, smart production, space. And today's topic, in which I will go a little bit more into details, is smart mobility. Here are a few facts about EDI. So we were founded in the 1960s. We are about 100 people right now working in 4 laboratories. So signal processing laboratory, space technology laboratory, robotics and machine perception laboratory, and cyber physical system laboratory. In the recent international evaluation, we were rated the highest in our field. We have invested several millions in equipment, state-of-the-art equipment. And as you can see in the next slide, we have more than 300 partners worldwide working together with us. We are working with the biggest industrial players in the mobility and automotive domains like Volvo, BMW, Mercedes, Audi, Infineon, NXP, Philips, and so on. Here is also a brief history about EDI. So in the 1960s, we developed our first computer in Latvia. In the 1970s, we developed the first microprocessor system for actually a rover, which was planned to be sent to the Mars. In 1980s, first academic wide area network. In 1990s, world's first digital analysis system for gigahertz signals. In 2000s, world's first event timer for kilohertz satellite laser ranging. And in 2010s, first self-driving car in Latvia. Of course, these are hard words. First self-driving car, because it's not like autonomous level 5. There are only autonomous functionalities, which we demonstrated. And here you can see this video for actual event. It took place in 2017 on 10th of May, when we presented the first self-driving car in Latvia. So it was equipped with drive-by-wire system, so you can control the car from your computer. And it was following some predefined route. And as you see, also some ministers attended this event, so we gave them a ride with the autonomous car. They were a little bit nervous, but after that, optimistic about all these developments. And yes, 1 year later on, we received a prize as the most significant achievement in Latvian science from Latvian Science Academy of Science. So smart mobility, as I earlier mentioned, we have several directions, and smart mobility is one of them, and actually quite strong in EDI. So smart mobility at EDI is split in 2 sub-directions. One is traffic monitoring. So in this case, we are developing different kinds of technology solutions, including hardware for traffic monitoring and optimization. This includes inductive loops, microphone matrices, also video processing solutions for, as it is in this example, where we have developed low-cost, very energy-efficient algorithms which are processing only those pixels which you can see on those lines. Therefore, this algorithm is very lightweight, and you can embed it into Raspberry Pi for pilot euros. But I will not go into details into this area. I also know that Transport and Telecommunication Institute is really strong in this area, and they will probably introduce also in this conference. I will talk in this presentation more about other subdirection, which is connected and automated driving. So in this area, we have this car or the platform for automated driving. It's quite clear that it's impossible for us to build a self-driving car from A to Z. It's too complex, and as it was mentioned in the previous presentation, it's very hard. There are thousands and thousands of researchers, engineers working on this autonomous driving, and it would be impossible for us as a relatively small institute with 100 researchers to build the self-driving car itself. So we are focusing on very specific key technologies which will enable self-driving cars, or which are necessary for self-driving cars in the future. So these key technologies we are working on, or technologies which will help to develop those self-driving cars, I have highlighted 6. So vehicle-to-X communication system, perception system, embedded artificial intelligence, drive-by-wire system, car-in-the-loop setup, and torque vectoring algorithm. In my further presentation, I will go into details about each of them. So first of them is torque vectoring algorithm. So this was developed in Horizon 2020 project called 3C Car. It's a huge project that you see, 53 partners from 13 countries with 53 million budget. And the aim of the project was to develop next generation of electrical cars, which means next generation battery cells, next generation powertrain, next generation embedded modules, and as well, as you can see, domain controller and algorithms. This was the part where EDI was participating and working on. So maybe you have heard that in modern cars, especially luxury cars, you can have more than 100 microcomputers inside a car. So the complexity to manage all those systems is increasing quite drastically. So our aim was to develop more reduce development effort, architecture complexity, and communication bottlenecks. Meanwhile, add some development capabilities, workflow agility, and optimization efficiency. In simple words, we wanted to gather all those measurements from those sensors, create with powerful computing unit different virtual sensors to add some new functionalities, new information out about the car. So here you can see in this slide, we created an algorithm which is called torque vectoring algorithm. In simple words, we developed algorithm which allows to control the power distribution between electrical motors between the wheels. And we embedded this solution in the below picture. You can see this heterogeneous system on chip system, which is combination of processor and FPGA on one chip. And we created a neural network which was embedded into this system. We were actually at that time one of the first in the world to do that. And also we received award from Latvian Academy of Science about one of the most significant achievements in Latvia, in Latvian science. So yes, we deployed this algorithm for torque vectoring, and it was tested on the picture. You can see the relatively sporty car with 3 electrical engines, and tested in different scenarios, so typical tests like moves test or ski pad test. Yes. So next one is vehicle-to-X communication technologies. So before I go into details with that, I would like to go back to the history. Actually, working on self-driving cars themselves, we started on 2010 when we heard that there is this Grand Cooperative Driving Challenge in the Netherlands. So we put our aim to participate in this event. So the event gathers the best teams of Europe who are working on vehicle-to-everything communication technologies, in this case vehicle-to-vehicle communication technologies, and test this solution in different scenarios. In 2011 we entered the competition, and the idea was for all teams to communicate between the cars and form 2 lines of cars and drive in the same speed, knowing the position of the cars, trajectory of the cars, distances of the cars, and so on. It was quite a success, and in 2016 they organized additional next event for this competition, and in this case they had already 3 more complex scenarios. So the first scenario was there is a fire truck coming, there are 2 lines of cars, and they need to split so the fire truck can go through. The second scenario was that there is 2 lines going into a highway. One line is blocked by the accident and the cars need to merge into one line in autonomous way, by autonomous driving, only by communicating with each other with these vehicle-to-X communication technologies. And the third scenario was to cross the junction for 2 cars, as you can see right now. There is communication between the cars to equalize the speed and do this junction in the most efficient way. So now we are still working on this. There are still some solutions available in the market already for vehicle-to-X communication technologies, but there are some gaps between these technologies. So we are now focusing to develop these V2X communication technologies: fail-aware, fail-safe, and fail-operational. which is really crucial for safety critical system as autonomous driving. And we got involved in this project called AutoDrive, which is working on self-driving cars, autonomous driving. Also work on powertrain, on perception systems, on different embedded modules. Semiconductor companies are very interested in this. But ourselves, we are involved in supply chain 5, which is related to communication devices. And here you can see what we have developed so far. This is the 3rd year of this project. So we have developed already the first prototype, and the ongoing testing is happening right now. So this is the device, and to enable this fail-aware, fail-safe, and fail-operational functionality, we are using 3 different protocols for communication, as well as 3 different bands. If one of the frequency ranges is blocked or there is interference, we can quickly switch to another one, enabling this fail-operational functionality. So the next one is perception system. Also, another Horizon 2020 big project with a lot of partners, huge European initiative to work on perception systems, to make those perception systems fail-aware, fail-safe, and fail-operational. So also in this case, we are working on these kinds of functionalities only for perception systems to simulate those kinds of situations when one of the sensors is failing, is not working properly. What happens, how car should behave? Should it park itself somewhere safely near the road, or should it continue the road by taking into account other measurements from other sensors, and so on. In this project, so we have deployed 3 kinds of sensors on our car or test platform. So the one is LiDAR sensor. We have 5 radars, 3 are aimed forward, 2 are backwards, and 12 cameras, as you can see in this slide. So sorry about the quality, I didn't have better video, but just to have the glimpse of what the car can see. So this is the LiDAR sensor. It can detect different objects, it can see into depth, they can recognize the distance of objects and so on. And this is what the camera is seeing. So detection of people, cars, road signs, and so on. So all this comes to embedded systems, so all the data we are gathering from the sensors, we need to process them. So the next direction we are working on is embedded artificial intelligence. So for this purpose, in our car we have deployed NVIDIA PX2 embedded system platform, which is also actually used in all Tesla cars as a processing unit. And it's quite powerful, 12 cores for CPU, 256 cores for GPU, and we are putting on artificial intelligence on this platform. Of course, you can also see that I have added in the slide that we have also a safety controller, which is our 3-core safety controller. This is industry standard for safety features, which we will also add to the car to enable this fail-aware, fail-safe, and fail-operational functionality. So this is what the car is seeing and how these artificial intelligent algorithms are working. So on the left side, there is the segmentation, so the car needs to recognize the cars, the road, bikes, people, road signs, and so on. And on the right side, you can see that this is fusion between LiDAR data and camera data to understand different kinds of objects and so on. 5th scenario is drive-by-wire system, which is like crucial system to control your car, which we have developed, and it's aimed for controlling from your computer, control steering wheel, controlling brakes, controlling throttle. This we are using to enable those autonomous drivings in some predefined tracks and paths. Last but not least, car-in-the-loop setup, which is a very useful tool which we have developed for testing different kinds of algorithms. So we are working in the car lab simulator, where we can deploy different kinds of sensors, test them into virtual environment, plan different trajectories, plan the path of where the car is going, and apply those controls directly to the car. So you can see in this video, in the simulator, the car is taking turn, and also in real life, it is connected, as this car is in the loop, connected to car, the car is moving its steering wheel as well as their wheels. And here in the back, you can see the setup where you can see this PX2 NVIDIA drive, also computer for Cargo Simulator, and other setups. So this is what EDI is doing, but also there are a few small initiatives in Latvia happening. So first I would like to say a huge thank you for our Road Traffic Directorate and LMT, telecom operator here in Latvia, who are supporting us quite well. So on your left you can see the Bikernieki racetrack or test track, which is provided to us. We can test the vehicle there for different scenarios, test for perception systems and so on. And on the right side, of course, is our supporter LMT, who provided us a car which we could use for different developments, testing and validation of those systems. Also, there is such company as Pilot Automotive Labs. They have developed this box which you can put on your roof of your car. It consists of several sensors which adds you ADAS functionality, so the car can see more around, it can brake when it's necessary, and make your car a little bit smarter from, let's say, level 0 to level 1.5 or something like that. And also they have developed this very interesting bootpacker platform, which is very cheap platform for enthusiasts who want to develop solutions for electric and automated driving. So if you are interested, you can contact them. And also, last thing in my presentation is Jelgava City, which is planning to deploy self-driving buses during one of the projects. So this is really briefly about what our institute is doing in this area. As mentioned before, we will have a demonstration car outside of this institute at the entrance after 2 o'clock, I think, during the lunch and after the lunch. So you can go talk to technical people about all the developments and implementations and so on. If I'm not mistaken, we will have also this car in the loop setup, so this could be also really interesting for you. So definitely go visit and enjoy. Thank you very much.
Any questions?
I have a question. Okay, thank you for your speech, thank you for your developing autonomous cars. And what do you think about Elon Musk's last electric truck? Autonomous and with pilot.
Yeah.
Thank you.
Yeah, what I think, this company is very famous with their PR and marketing strategies. So they are first announcing everything and then starting to work on this, and usually they are quite far from actual result. But as an initiative, I think this is really good idea. From my perspective, the first applications where autonomous driving could be introduced are taxis or these highway trucks, like platooning applications and so on. So as an initiative, I'm happy for that this is moving forward. But from technical point of view, they haven't provided much details about the truck itself. So it's really hard to judge, yeah.
Okay, thank you.
Thank you very much. Thank you very much for you. If you have the time during the day, maybe to ask something, Dr. Kasper. And thank you very much. Now we have the break, and I want to announce a very short break, 10 minutes for next plenary session with 2 distinguished speakers. Only one special appointment for post-action participant. Please, your coffee powder will be in the room 221st on the 2nd floor, and after it we will announce raising your phone for meeting. Yes? Then conference will continue for 10 minutes here in this place. Please be with us.
Меня-то? Хорошо, я знаю, где вы. Хорошо.
Ой, здрасте. Как жизнь? Нормально? Как жизнь, говорю. Нормально?
Good to see you. How are you? Good, yeah. I actually meet Lucky. Supposed to be here. Give me 1 minute. Yeah, no problem. Yeah, we'll catch up. Yeah, 2 days.
Вчера прочитал.
Couldn't say anything.
But in the end, you managed? They made you pass?
They didn't, just night morning and went to another flight with another airline.
Which airline were you flying with?
Say he's right.
Okay.
It was crazy. They didn't give us any refund or anything.
No,
And then they would have to go when we went to the airport with the other flight. We came because we were going to lose the return flight.
Oh, this was when you were going?
Yes.
Oh, not when you were coming
No.
back. Oh.
They have, in all airports.
Because to this friend of mine, it happened when she was supposed to come back. It's like, if you're denied boarding, and maybe I don't even go, it's like, fuck it, at least I don't go. But like, she was there, and she was supposed to stay there, like, I think 2 or 3 days more, and she had to pay everything for herself. I was like,
But no, they.
I've only seen her picture on Skype.
Πού είσαι, Τζορτ?
Τι κάνεις, Νίκο, καλά?
Τι κάνω, μια χαρά, μπλα. Πώς πάει? Θα μιλείς?
Ναι,
Μόνο δεν σε βλέπω, τι θα γίνει?
Εντάξει, εσύ τι κάνεις, καλά?
Καλά, καλά. Το Μίλτο το ξέρεις, Μίλτος. Γιώργος. Anyway, τι θα ρωτούσες? Δημήτριος,
πού θα είμαστε?
Επάνω λέει. Ωραία. Είναι όλοι μαζί απάνω.
Давайте познакомимся.
Олександр, я сам професіональний льотчик, як літавший.
Хорошо, как появится, позвоните, пожалуйста. Хорошо, все. Я просто хотел вас еще познакомить с директором нашего национального дизайна, да, вот этой организации. Факт, а может быть, да, я знаю, что не да, он лучше собственно говоря, сейчас вот
Да, пожалуйста.
Ему не хватает только на вот где 500 часов на год, тогда лучшая компания будет работать на том пути, на котором будет работать, не на цех. А механики и электроники, почему у нас и сдают экзамены профессиональные. И вот не получится. Даже не бывает, и параллельно
So, dear participants of the conference, you are welcome to take your places. Of course, you could take a coffee and cookies with you. Yes, as the coffee break was quite small. So one more time, we are starting the plenary session part 2.
Товарища Жукова заинтересовала. Ну как?
Александр Владимирович. Okay, so welcome to the plenary session, part 2. So as it is planned, we will have two amazing presentations regarding artificial intelligence. So first of all, let me introduce myself, because I'm let's say, will sit here and manage all the processes. So my name is Mikhail, and I am a Dean of Computer Science and Telecommunication Faculty here in Transport and Telecommunication Institute. So to continue our plenary session, we have another guest. Actually, we have two guests, and both are from France. So I think we will have amazing presentation, and the first presentation will be provided by the professor, Dr. Eric Gossier. Probably he will present himself in a very good way, but he is going to talk about learning representations for clustering, some solution to an ill-posted problems. So for each presenter, we have 40 minutes plus 5 minutes for questions and for very small discussion, but as you saw, after we have lunch, so you will have plenty of time to communicate face to face. So one more time, please welcoming Professor Eric Gossier. And sorry, some notes. Someone has forget the following thing near the coffee machine here. So it is here. You could come to me and ask for it. Okay?
Thank you. Hello, everybody. So I first would like to thank Mikhail and Irina for having invited me to this conference and having given me the opportunity to present part of my work. So I'm a computer science professor at the University of Grenoble, and I'm currently heading the Artificial Intelligence Institute in Grenoble, as well as the Computer Science Laboratory. So today I'm going to talk about a particular problem in data science, that is clustering, that is also quite often referred to as unsupervised learning. And I would like to present you a few ideas that have been developed in the recent years in following the advent of deep learning and representation learning methods, in order to try and solve some of the inherent problems that clustering has. So this work is a joint work with Mazia Moradifa, who is a PhD student of mine, and Thibaut Tonnet, who was a postdoc and who is currently working at the lab. Part of it was also done in collaboration with two master students and with two colleagues, Aurélien Bellé and Marc Tomasi from Lille. So, what is clustering? So clustering is one of the most used technique in data science when you don't have any label. And it's a technique that is used to try and structure a collection of objects. So let's assume you've got a collection of objects, but there are many of them, and you want to get a better idea of what is in your collection. Then one way to do that is to apply clustering techniques in order to identify groups of objects which are similar to each other in your collection. And like that, you can then have a better view on what's in your collection, focusing on the groups of objects that may be of interest to you. So to do that, you have to define what is called the similarity or dissimilarity measure between objects, in order to say whether they go to the same cluster or not. And you often have to also define the number of clusters that you want to get from your clustering algorithm. So this can be, there are methods to identify almost automatically this number of clusters, but they say in general this is a parameter of the clustering algorithms. And above all these clustering algorithms, they assume a given representation. Okay, so you start with a representation of your data, and then you run your favorite clustering algorithms. So there have been a lot of clustering algorithms that have been proposed. In this talk, I will focus on one of the most popular one, k-means, but several aspects of this talk do extend to other clustering approaches. So the fact that we have a given representation is due to the fact that, okay, you've got objects, for example, images, then you can try and extract different features from the images, and then you've got your representation, and you start clustering this representation. Or you have textual documents, you have text, you extract words, back of word representations, then you have vectors representing the objects, and you can run your clustering algorithm on that. And same thing, for example, if you have logs of sensors embedded on machines, then this will naturally define the representation you will have. Thank you. Okay. So as I said, I will focus on this talk on k-means, which is a very popular clustering method. And the idea of k-means, this algorithm works as follows. So let's assume that you've got all these points on the upper left part, okay, all these grid points, and you want to cluster this collection of objects. So each point represents an object. You want to cluster this collection of objects into two clusters, into two classes. What you do is you just select 2 points, so the red point and the blue point, randomly, and then you assign each object to the closest point. So you compute, for each object, you compute its distance to the 2 representatives that you have randomly selected, and then you say, well, my objects, so for example, you will have the red points that correspond to the objects that are closer to the red representative, and the blue points that correspond to objects that are closer to the blue representative, okay? And like that you have a first division into 2 clusters. And then you iterate this process. From these 2 classes, I will now build new representatives by taking the center of gravity of each class. I'm just taking sort of the average of all my data points, red points. This will give me a new representative. I take the average of all the blue points, new blue representative, and I reiterate. And of course, the center of gravity of the red points will be closer to the points that are on the lower left corner of the data points than to the upper left corner, so that after just a few iterations, you will end up with the 2 groups that are given in the last window. Okay? And if you look at the original data collection, this seems like a reasonable clustering result. Okay. So what we have done basically by doing that is we have optimized the distance between, we have looked for representatives such that the distance between all the points to the closest representative is minimal. And so this can be written in this form, where basically what you try to do within the k-means clustering algorithm is you try to identify representatives such that, so points, such that the distance for all the points so that the distance for any point to the closest representative, the sum of this distance is minimum. Okay. So yes, just one remark here is that within this minimization problem, you've got this quantity Cx that corresponds to the closest representative to the point x in the set of representatives. So you've got an argmin that is evaluated minimization. So now I started by saying, okay, clustering, the problem with clustering is that it is an ill-defined problem. The main problem with this is that if I give you a collection of documents and I ask you to come up with three clusters for this collection, you are very likely to come up with a solution that is different from the one I will come up with, or from the one another person will come up with. There is no clear definition on what is a good solution, except for the fact that it has to be minimum according to this problem. By the way, the minimization problem I mentioned cannot be solved explicitly. So there are a lot of local minima, and we are bound to in practice to end up on the local minimum. So what I mean by my previous remark is that the solution of the clustering problem is subjective, in the sense that the clusters that are going to be of interest to you will be different from the clusters that are going to be of interest to me. For example, if you've got a collection of documents that describe a machine in a company, you've got both a technical description and the price and the market and so on in this document. If you ask an engineer to cluster the documents, the clustering will be based on the technical aspect of the machines. If you ask a marketing people to cluster the documents, the clustering will be based on the markets that are targeted for each machine. So definitely clustering is subjective. As I said, it's also a non-convex optimization problem with potentially several unstable solutions. And in essence, there is no such thing as unsupervised learning. And people realize that now. There have been a lot of work on that. But if you don't add any information to this problem, then you have basically an identified problem. So the goal here that I want to pursue is try to solve propose solutions to these different problems. So I will skip this one. So just another illustration of the subjectivity of solution. If you just give to people those images, what is the natural grouping of these objects, you could have a grouping that is based on the family and school employees, or a group clustering process that is based on male-female separation. So the advance, as I said, the advance of deep learning and representation learning proposes to, opens the door to learning representations that are specific to a task. And that is very interesting in this case, because as I said, we start with a given representation that is maybe not at all appropriate to the clustering process we want. For example, if we have a lot of technical elements and marketing elements, and we are just interested in the technical clustering, then part of the representation that we are using just represents noise for the objective we have. So the idea that we want to propose here, and we are not the only one, not even the first one to propose that, is to learn representations at clustering time and be able to get to better representations for the clustering task we are interested in. And then the second idea to solve, but this does not solve per se the subjectivity problem, the other idea we want to put forward is that we need to integrate user input to bias the representations according to the user needs. And a third point I want to mention is that if you look at the K-means algorithms, you have these two steps. First, you assign objects, documents to classes, to the class corresponding to the closest representative, and then you update the representative. This corresponds to two optimization steps that are independent of each other. And in many cases, one can gain by trying to do a joint optimization rather than just this two-step independent optimization. a very simple analogy is a chessboard. If you look at on a chessboard, so you've got a knight, and the knight can only go first in one direction and then in the other direction. Okay, so you've got one direction, then another. And if you compare the movement of a knight to the movement of a queen, you can see that the queen can go in all the possible directions. It's a bit like that for this optimization. When you are on a surface that you want to optimize, either you have the knight approach where you optimize in one direction and then you optimize in another direction, but you can only go to a certain point like that. I mean, in theory, you can go to all points, but if there are certain points, you may be stuck on one dimension. If you have the queen approach, then you can go in all directions and escape away from those certain points. So there is, in theory, a priori something to gain by doing things jointly. Okay? So, the first part of my talk will be to present you this deep K-means approach, where we do jointly representation learning and clustering, and where we propose a joint optimization problem, and we solve it jointly. So, to learn this representation, we are going to use what are referred to as autoencoders, and this is a very important and useful ingredient from the deep learning and deep neural network community. So, an autoencoder is basically a neural network that from some input is going to predict the same input. So you feed your network with an input-output with the same input-output. Sorry, I've got to take care of the mic. Thank you. Yes. So this is basically no, there is no pointer. Yes, there is. So this is basically an autoencoder, where you have the first part of the neural network that takes the input and tries to project the input on a lower, usually on a lower dimensional space. And then you've got a mirror network of this input of this first network that takes this projected input and tries to reconstruct the output. So the network is learned with X as input and the same X as output, and the goal is really to try to have a network that projects onto our dimensional space, then back to the original space, and tries to reconstruct your input. And by projecting here, this projection here is the representation that we are going to use. By projecting, I can get rid of all the information that I'm not interested in my particular clustering task. For example, all the representation pertaining to marketing if I am only interested in technical clustering. Okay? And so what one does is just take this autoencoder and then do the clustering not in the original representation that we have in the original space, but in this embedded space. And so the representatives are learned in this embedded space. Okay? And so it turns out that I will just try to show you the final objective function. So the final objective function is just, I'm trying to minimize over the set of representatives and the parameter of my network, a reconstruction loss and the traditional K-means loss in the embedded space. Here I'm working solely on the embedded space, and here I'm trying to also I'm trying to compromise this clustering loss with a reconstruction loss. That is, I want the representation that I'm using, which is h theta x for the document x or object x. I want this reconstruction to be precise. Why do I want that? Because, of course, if I take any representation, then that is not linked to my original representation, then in fact I can completely minimize that and have a zero loss here, simply by projecting everything on a given on the same vector, for example, the null vector. So I need here to say I do want to keep some of the characteristics of my original document. Okay? And so basically this is the kind of losses that are considered in this new reformulation of the problem when you do the clustering in the embedded space and you learn the representation jointly with the cluster representatives or with the clustering parameters. Okay. So now I say that we also want to solve the problem jointly. In fact, this problem had been considered before, and the people had come up with a solution to solve this problem that is based on this night approach that I mentioned. That is, they did independent optimization on the different on the clusters and the update of the representatives. So what we wanted to do was to go one step further and try to propose a joint optimization approach to that. And this can be done very easily by reparametrizing the function that we are considering with an additional parameter and control this parameter so that when, for example, the parameter tends to infinity, the behavior is the one of the K-means algorithm. So let's just, if we have a function that behaves like that, that is 1 if the R is indeed the closest representative to h theta x and 0 otherwise, then we can reparameterize our problem, and in the limit of this reparameterized problem is exactly the problem we want to solve. And so we just need now to find a function that is differentiable and that can be written like that, and there are several functions we can use. This is a function that is inspired from the fuzzy clustering fuzzy C-means algorithm, for those who are familiar with it. But this is a function that we are advocating with is just a variant of the softmax function. And just using these kind of functions, it's very easy using these kind of functions, you can fully differentiate your problem, you can have a joint approach. There is no problem with the argmin any longer. This function is differentiable everywhere. And so you can jointly solve the K-means clustering problem. Okay, so I'm now going to illustrate the kind of results we obtained with that. So just to summarize, what we have seen is how to reformulate your clustering problem so that you can learn representations using autoencoders and have representations that are better suited to your objectives, and how to rely on fully differentiable functions for that, so that you can do a joint optimization and so that you can avoid problems when computing derivatives and updating the parameters. So we used, just a few words on the additional parameter alpha that we introduced. Alpha plays two roles in fact. So when alpha tends to infinity, it gives the approximation of out clustering of the problem of the K-means. So if one takes alpha sufficiently high, then one will get the exact K-means solution. And it also plays a role of the inverse temperature in the deterministic annealing scheme. So deterministic annealing is something that is different from simulated annealing, in the sense that you also reparameterize your functions, the functions you want to optimize, in such a way that when alpha is 0, for example, your function is convex, so that you can identify the global minimum. And then you increase, and then this global minimum is the new point for the function when obtained by slightly increasing alpha. So, and then you find a new local minimum with this increased alpha that serves as a new starting point for the function, for the minimization when you increase alpha, and so on and so forth. So like that, you keep track of a series of local minima that are likely to be good. I say likely because there is no technological guarantee in all cases, that are likely to be good and to lead you to a nice local minima at the end. So this technique was developed at the beginning of the 90s. It has been used in several domains, particularly in vector quantization. So we tried both approaches by either by setting alpha very high or by trying to keep track of the local minima by increasing alpha over time. Okay, just to give you an idea of the kind of algorithms that we implement to do all that, it's just that. It's no more complex than that. So by using the existing libraries on deep learning and deep neural nets, all you have to do is that. The tricky part is here, that's the gradient descent update, but they are automatically computed. You don't have to worry about that. So you see that finally the code that we developed is very, very minimal for that. Sorry, it doesn't mean that it is fast, okay? The code itself is small, but this kind of development takes time in order to be able to converge towards the correct solution. So we have tried this approach on different data sets, on 2 text data sets, 2 image data sets, using traditional k-means, using an approach where you do autoencoder plus k-means, and using the previous approach that was proposed in that direction without joint optimization, and our approach. Okay? And with different autoencoders, with different architectures and so on and so forth, I skip the details here. Just to give you an idea of the results. So the most important part is, so these are the results obtained with say, the baselines, k-means and autoencoder plus k-means. So k-means is just, I take the original representation and I do my k-means algorithm. Autoencoder plus k-means is, well, first I learn another representation than the original one, and then I do the k-means on this representation. And you see that the gain obtained by learning a representation is very, very substantial. So, as I said at the beginning, there is no reason to believe that the representation we have is the best one for the tasks that we are handling, and indeed, one can do way better by learning the representations. And one can even further improve on this learning representation by learning a representation that is indeed appropriate to clustering. So in that case, we are jointly learning the representation and clustering. So we are sure that the representation we are learning is tuned towards the clustering task. And and between these 2 approaches, we gain by jointly solving the problem. Okay, so that was the first part that I wanted to mention. Now I want to focus on the second problem that I mentioned, and which is maybe the most important problem, and all that was just the first step for handling this most important problem. This most important problem is biasing the representations, and here I will focus on text. And as I said, the clustering results, they do depend on the different on the users and on the user needs, and so the only way to be able to bias to get results that are adapted to each user is to have some kind of interaction with the user. You need to get some information about what the user wants, otherwise there is no way, of course, that you are going to propose a clustering that is fully adapted to the user needs. So what are the type of information the user can provide? So there are traditional constraints that have been used in clustering that are called the must-link and cannot-link constraints. For example, you can ask a user to look at a set of documents and tell you whether these 2 documents should be in the same clusters or not. Okay? And if they should be in the same cluster, it's called a must-link constraint. If they should not, it's called a cannot-link constraint. But this is time-consuming, and this does not always improve the results. What we're more interested in here is a more natural way for users to express their needs, and what we are investigating here is the possibility that users just provide a set of keywords describing the different clusters they want. Okay, for example, here we could have users saying, well, I want two clusters, one talking about nation and freedom, and one talking about multicultural equality, another one about refugees, immigration, another one about environment and climate. So you just provide the users the ability to give you 3 words describing each per cluster, describing the different clusters they want to. And that's the kind of information that we're going to look at. So I will skip this one. So how to take into account this this information with the framework that we proposed so far. So this part here, sorry, is what we have seen before. You've got your document, the autoencoder. This is the representation that you have learned, and you do the clustering in the embedding space, in this representation space. Okay. But now we have additional information that describes the kind of clusters we want. So one way to take this information into account here is to say, well, I take all my input documents and I'm going to bias the representations towards the seed words that we are interested in. Okay? So the documents that are close to the, if they contain words that are close to the seed words provided by the users, I should give more importance to this word in the clustering process than to other words. And like that, I'm sure that I will have a clustering process that is more in line with the user needs. So you can do that by masking. So for example, you just take your document and you just retain the words that are in the seed words, and then you compute the same encoded representation as here, and you just try to say, okay, this. So here is the representation in the embedded space of my document filtered out by the seed words, and I want the representation of the document that I'm going to use for clustering to be close to this one. Okay? So instead of filtering, I can also weight the words according to the proximity to the seed words, but the idea is really this representation that I'm going to use for clustering, the representation of documents, should be close to the seed words, if, of course, the document is close to the seed words. Okay? So that's the first possibility to bias your documents. And another possibility is to say, well, instead of biasing the document representation, what I can do is I can try to bias the representatives. And I want the representatives to be aligned to the different seed words. As the user provided seed words per cluster, it means that the representatives of the cluster I'm going to have should be close to the set of seed words given for this cluster. So what I can do is just bias these representatives. So same as before, this is similar to what we have seen in the first part. And here we just take the seed words, compute the representation, get an embedded representation from them, and forces the representatives that we have here to be close to these seed words. So, the optimization problem in that case can be formulated as that. So we have the full optimization problem that we had in the first part, plus a term that is saying I am forcing the representation of the representatives to be close to the representation of the seed words as well. Okay. So what we did was use the same algorithm as I mentioned before that we and others you can use any deep clustering algorithm you are interested in fact, and we added this different element here in our optimization problem. So in that case, sorry, I have not written the optimization problem, but it's a similar one. It's a similar optimization problem, and so this leads us to different versions of our clustering depending on whether we do these embeddings at the document level or at the representative level. And then, of course, we can play with the kind of similarity or dissimilarity we are using here. So here it's written with the Euclidean distance, but we can also take into account cosine dissimilarities and so on and so forth. The cosine distance, for example. Okay, so these are just a bunch of a bunch of parameters, hyperparameter settings. We have tested this approach on five different text collections, where you see the number of documents that are involved in that and the average document length in terms of words, I think, or sentences, I don't remember. Okay, and we have tried several approaches on that one. One difficulty to evaluate these methods is that you need seed words, and so it's a bit type. As we did not have seed words for all these collections, we proposed an automatic method to compute the seed words by simply looking at the different classes, extracting the most frequent words from these classes, and use them as seed words. And we'll come back to that later. To check whether this method was correct, we also did a human experiment involving annotators, but just on one collection, asking them to extract seed words and compare the seed words we obtained automatically with the seed words we have obtained with humans. So these are the results we obtained. So basically, you see that these are the results of DKM, which was the best deep clustering algorithms we tested on this collection. So it's without using additional information. Okay, so the best results here, they are around 68%, and so on and so forth. So you see that it depends on the collection. And now these are methods that are taking into account seed words. And you see that in different collections, so here you don't gain a lot, you gain 4 points, 4 to 5 points, but in these collections, for example, you gain quite a lot. And here you don't gain a lot, here you gain quite a lot, and here you don't gain a lot, even, I mean, this is on par with this one, for example. So, all in all, what this shows is that nevertheless, the seed words, they do contain useful information, and they can help you improve the results and bias the results towards the humans. That's one point that we do toward human needs. That's one point I will come back later. Okay, and among the best results, the best one was these two ones in terms of macro averages overall. If you look at the number of seed words, you see that, so this, we tested the results with 3 seed words per cluster up to 5 seed words per cluster, and you see that, okay, there is some variation, especially here, but in many cases, 3 seed words seems to be enough to obtain good results. So I will skip this one. Yes, and last experiment that we did was to compare whether the seed words that we used for your evaluation that were automatically developed because we had no choice, no other choice, were somehow representative of the kind of seed words humans would propose, and so we compared the overlap between the automatic and manual seed words, and the overlap. I don't have sorry. You see that the overlap, qualitatively, you see that the overlap is quite important. And in terms of performance, we had very similar results, with the human seed words giving slightly higher results. So the difference with the human seed words with respect to the clustering approaches that would not take into account seed words was even more important. Okay, so, okay. Just before I conclude, there is one point one experiment that we're currently conducted at a larger scale is to try and compare different approaches to compute with humans, to come up with seed words, and to compare these kind of approaches with the approach in terms of time, with the approaches based on muscling and canonical constraints. As I said, muscling and canonical constraints, they do not lead to results as good as this one in terms of performance, but they are a priori faster to establish by humans. So we are just measuring all this time right now. An important point is, so we were able to show that, okay, you gain in performance by doing that, but an important point is we would like also to see what is the perception of humans when they look at the results according to the needs they have expressed about. So just to conclude, I hope, so my goal was to show you the kind of ideas that are going around on clustering currently, and these ideas are exploiting the recent advances on deep learning and representation learning. And so we have proposed a fully joint approach based on learning document representations that partly addresses this. And sorry, this is not entirely correct, because the most important point that I wanted to mention here is the fact that we were able to propose to partly solve the subjective problem by relying on information provided by the users. Maybe just one last point is that we were not able to, so if we have tried to fully exploit the recent development in deep learning and representation learning, I'm still very frustrated with the kind of autoencoders that people are currently considering for documents. They are very poor autoencoders. And basically, most of the document representations, they are weighted averages of weight of word representations, and it's very difficult to go beyond that. There is one recent work that tries to go beyond that, with hierarchical LSTMs, and that we're trying to explore in this context, hoping that we can definitely gain and get even better results by relying on a better representation of our documents. Okay, thank you very much.
Okay, thank you very much for an interesting presentation. I believe that it's great input to artificial intelligence solutions, but I believe it will be developed further. Okay, as we are running a bit out of the time, so only one question is allowed. Who would like to ask Eric something? Okay, I see the person, so just wait a second, and not so fast, please, the floor is yours.
Hello, thank you for your presentation. It was really exciting. And I wanted to ask one specific question about your filtering the text with the seed words. Did you use some threshold for filters? You just compared all the words by the standard embedding, maybe? Yes.
So,
how you? It's about your seed words using for making better autoencoder.
Yes. So the seed words, they don't change the autoencoder.
I can see. I wanted to ask how you filtered your text by the seed words. Was the threshold for the filter, or you used only the words with the same means?
Very good question. So we tried both. So for example, in this case, we just filter out all the words in the document that are not in the set of seed words.
Oh, see.
So that's the first approach, very aggressive as a filtering approach. And the second approach is to say, I'm going, and that is what is written here, I'm looking at the word embeddings of the words in my document and the seed words, and I'm just taking a representation that is based on the distance between the word embeddings.
Yeah.
It turns out that in our experiments, there was no difference between these two approaches. So even this very aggressive approach where you say, I remove all the words that are not in the seed word set, gives the same results. And this means that if you have a document that is not, that does not contain any seed words, it will not get clustered. So you need to add a garbage collector in that case, but I mean, it seems to work pretty well. You have to bear in mind that we, for the automated seed words, we use very frequent seed words. And so this definitely helps this strategy, but they are very close to what humans propose as well. If they are interested in very specific seed words, then they are more or less they intend they want the seed words to appear in the documents they are going to look at.
Okay.
So this aggressive filtering approach works in practice.
Okay, thank you very much for your question. Again, I'm very sorry that we are running out of the time, but you could do discussion during the lunch with Eric. But Eric, please don't sit. Don't sit, we have a present for you. So thank you very much for a very interesting presentation. Okay, Okay, so, and we're kindly asking the next speaker. First of all, just wanted to notify that I'm not so good in French. That's why we are asking Professor Dr. Fabian Monterey. No? Ah, okay, so, sorry, as I have said. Oh, okay, thanks a lot. Yes, and the professor will give us a presentation regarding vehicle absolute localization from vision using only pre-existing georeferencing panoramas. Okay, so professor, you are welcome. The floor is yours. 40 minutes ahead.
Okay, thank you for the introduction, and thank you for the organizer to have proposed me to my speech to be a keynote, and also a big thank to the Institut Français de Lettonie who made all this possible, because it's from their initiative that I'm here at this conference and meeting several laboratories here. So, since my talk is actually a keynote, which was not so clear in the beginning, I kind of extended a little for it to be not as specific as the title is, or as the abstract is. So I will begin with some more general aspects on deep learning for intelligent vehicles to make it more a keynote. So first of all, I should present myself. So I'm professor in Mines Paris Tech. Mines Paris Tech is one of the best engineering schools in France. And in this school, I am a professor at the Center for Robotics, for which I'm also the deputy director. And this Center for Robotics is not that big, like maybe 30-something people. Even if the name is only robotics, actually the main focus of the laboratory is autonomous vehicles, intelligent transport systems, but also on robotics, specifically the collaborative robots, intelligent robots aspect. So here you can see some of the recent or less recent works by the laboratories. For instance, he's gone. I have been the advisor for 2 PhD students working for Aldebaran, the makers of the Now robot. So that here you can see on the lower left paper for which I was working on localization also. Oops, why is it? It's not moving. Okay, so maybe because it's not moving, just to say that we work a lot with companies, especially big French companies like Valeo, Peugeot Citroën, Safran, Thales, and SoftBank Robotics, which is actually in Paris for its research. And also we have several collaborations worldwide with Berkeley, Shanghai Jiaotong, and BFL. Okay. So as I said, I will first make a small introduction to artificial intelligence for intelligent vehicles. It was already presented a little in the speech, the second keynote speech, but I think it's worth to recall that in fact there is some kind of continuum from the no intelligent at all level 0 to the supposedly 100% autonomous vehicle advocated by Google in the beginning, level 5, which will probably never appear, or that's my opinion. But and I think it becomes the global opinion. But actually, there is a full list of intermediate automatization, and actually, even now, many of the cars that are on the road have some automation. And actually, I'm now nearly never using my feet on the pedals because I use adaptive cruise control for handling the distance to the car in front of me and stopping. And So we have already a lot of automatization in existing cars. So now the problem is, will we go to actual level 3, which means that hands off, which means we can legally not keep the hands on the wheel, on the driving wheel? Will we go, and I hope very soon it should be possible, to level 4, where we can even look somewhere else and we don't have to supervise what's happening? And I don't think the pure mind off where there is not even driving wheel pedals is for very soon. But on the other opposite, I think the level 3 and mostly 4 will be available not so far away, but in very restricted conditions. For instance, level 4 autopilots restricted to motorways or these kind of things. And so this is just a recall that in fact this is just some evolution, natural evolution from existing functions that are already in everyone's car, like, well, not everyone's, but in high-end car. It's very common to have lane departure warning or blind spot monitoring, or even adaptive cruise control, which with a radar will handle the longitudinal control for you, or lane keeping even. So actually, if you have the lane keeping and the adaptive cruise control, you have somehow an automated car, except that you're supposed to watch out and it will not overtake by itself. So somehow all the bricks are here. So now the research part on this is to put more intelligence on the whole system. And so the whole system, this is just to insist that an autonomous vehicle or just intelligent vehicle is just a mobile robot, except people are inside. And so there are 3 boxes in a robotic loop: the perception box, look around, the reasoning and decision box, and the action box for control. And so essentially the intelligence part will be and is in the perception part, and a lot of progress was done on this with deep learning, so the automatic analysis of surrounding and also other aspects, for instance, localization I will talk about. And I want to insist, and I will say a little word if I have time at the end, on the fact that now the focus is kind of shifting to putting intelligence on the upper right part, which is the planning and the reactive behavior. Is it possible to learn this? So now I will present the very specific part for which I proposed an abstract and an article, which is about ego-localization with vision only and without need to record images beforehand on the same place. So first of all, so this was a work by a PhD student from VDECOM, which is a research institute in France, and it was co-supervised with Guillaume Bresson from VDECOM and my colleague Cyril Julie. So first, maybe not all it's so clear for everybody. Why would we need to use images to do ego-localization? First of all, what do we need to localize? This can be a bit obvious. For intelligent functions, you need the car to know roughly where it is, on which lane, how far from the next intersection, and this kind of thing. So we need ego-localization in an intelligent car. And I mean absolute ego-localization, localization on the map. But we do have GPS for this. However, you may know or may not know that the GPS is not so precise, and in fact there are often outages of GPS, especially in very central downtowns, where you have very high buildings and there is occlusions for the satellites, and so sometimes you don't have GPS position. Or if you're underground, in a tunnel or a parking, no GPS clearly. So actually it's interesting to investigate other means of ego-localization to mitigate the case where there is no proper GPS working. So also one other thing is that the GPS would give you directly only the position and possibly the speed, but not the orientation, or not directly. It will several localizations. So what we want really is to have the position and orientation of the vehicle from vision. And other alternatives would be odometry, like you would look at the wheels, how many turns the wheels do, but it's not so precise, and it's impossible for it not to drift with time, so you have cumulative errors, so normally you would have to reset this regularly. Or you could have inertial measurement units, but if you want it very precise, it's kind of very expensive. Like for instance, the one that my colleagues have on their mobile mapping system is like 30 kilo euros, like very expensive. You would not put this on the car. Of course, you could have a low end, maybe combine them, it's another possibility. But so anyway, a lot of people, because there are also other applications, are interested on how can we localize from just the vision of what we have in front of us. So this is the visual echolocalization problem. You have an image on the left, what's in front of your car or a pedestrian or whatever, and you want to know where you are on the map, and not only where, but where are you pointing to? Okay. So there are many techniques, and I will not give a full talk on all these techniques for this, that use that, but usually what you would do is you would collect many images along the street you want to localize later, and then you would do some comparison between the query image and the pre-collected images. The problem is then it means it will work only where you have already been collecting images. So that's why we were, and at the same time, we know that, for instance, Google Street View or the Baidu equivalent, they have made available panoramas of at least 3,000 city centers in the world, and it's quite dense. On the top you can see some of the, like each of these is a place where there is a panorama in the center of Versailles, in Paris. So actually, normally it's about every 10-15 meters, so it's rather dense. And so we were thinking, well, why couldn't we use this as the pre-recorded geolocalized images to localize the query image? So what you need to know is that actually what it is in every of this position is something like that, which is a 360 panorama. But in Google Street View, they have also a coarse depth panorama corresponding, which is very useful. I will explain that later why. So how can we do this? So if we try to match directly the query image to something like that, we will have a lot of problems because there is distortion here. So the first thing is that from this, we can easily generate any rectified image looking in any direction with any focal length, so you know the target focal length of your camera, and you can generate as many images for each panorama. So then it will make you a basis of images, and for each one you know exactly the position, because it's known here, and you know exactly the orientation, because you know the orientation here, and you know which direction you were pointing for each image. So it's easy to generate image in any direction around each of the street view panoramas. Then we still have a problem. I cannot speak the intermediate work here, that, okay, 10 meters is dense, but maybe not dense enough somehow. And sometimes it's even 50 meters. So we discovered in the first test that it was maybe not enough to have a precise enough localization. So what we discovered is that it's possible not only to generate virtual views in any direction around a panorama, but we can take two successive street view panoramas, and because we have the depth, we can compute virtual views from any intermediate position between the two panoramas. Well, the problem is, of course, if you're too far from the first panorama, you don't know what would be there if you would be 4 meters later. So the generated image, they have some missing pixels. But still you can generate and you can complement the panorama from Google Street View by virtual views from virtual position in between existing panoramas. So, so then what we can do is just apply standard place recognition methods, which are used for image retrieval commonly. So you could essentially what we do is on every of the generated rectified image we compute some key points. Well, actually maybe not this one because I think the final one were others. So you would have interest points in all the generated images, and you would compute what is called the bag of visual words, so it's the visual equivalent of bag of word in text, for each view of each panorama or virtual panorama. And then you have a feature that describes each of the thousands of images that you have from your city or from your street. And so the global way it works, you have this offline where you use the pre-existing Google Street View panorama, you synthesize view all around from the original panorama and forward a few meters. You have all these key points, you compute by the word. This is done offline once for all. And then what happens on board, you have the query image from the camera, you compute the key points in there, you compute the bag of words, then you do the matching. So this will provide several candidate views from those datasets which resemble somehow the query image because they have similar bag of words. And so here you have one or several reference views which are selected from those with the matching. And then you can even be more precise because you can then compare the position of key points actually maybe this one is not placed correctly. So actually the comparison would be with the reference image and the query image key points. Actually I should have put here. And from this you can be more precise. For those of you not familiar with that, for instance, if you have these two images, you can find the matches between some key points in the query image and some key points in the reference image, and see what's the displacement between the two. And from this, you can estimate the translation and rotation, and so you can know what's the vector between the reference position and the query position. So in this way, you can have not only you can be more precise in the localization. So then we've been doing, well, the PhD student has been doing an experiment to test this. So limited in Versailles. So they had this experimental car with cameras. Actually, we tested several setups, either the facing camera or cameras more looking on the sides, because quite logically, the buildings around you are probably better ways to recognize where you are than just the road and the bus or whatever in front of you. And also, the car is equipped with a RTK GPS, which is a specific GPS which has centimetric precision, and so it provides the ground truth to know what is the actual real position. And then what we obtain is this kind of thing. So here you have in red is the original Google Street View panoramas. In blue you have the virtual position where we have generated also virtual view intermediate. And then we have the ground truth of the vehicle, which is the red line. and the two blue and green, which are the estimated trajectory. The blue is using only the original street view panorama, so you see that the blue is a bit farther and moving around, and that, thanks to the augmentation with intermediate views, you are closer, the green is closer to the red, and you can see here the comparison, while somehow you get 3 meters error instead of nearly 4 meters error on average, and in the end you get something like 70% of the position have less than 2 meters error. So this shows that the goal is somehow attained. It's possible with if you are in a street where you've never been, but you have the street view panorama there, to localize with several meters error, which is comparable to GPS. So now, what about deep learning? Actually, there was a paper several years ago which proposed to use deep learning not to just look what's inside the image, but to infer from the view the position and orientation of the camera. So this paper, which you nicknamed as PoseNet, was by Kendall et al. In 2015, and so what we tried is to adapt this to our problem. So we simplified, because they were using 6 degrees of freedom, we just used 3, like we suppose we're on a flat ground, and we care only about the XY position and only one U angle from the north. And so we load this. We also do some modification because here the convolutional network is learned by transfer learning, which means initially it's the one that was trained on ImageNet for image recognition. So they had used Inception. We tried to a more recent one, which is RelStat. And then we train this stuff on all the generated rectified views, the same that we applied the classic computer vision method. So in the end, we were somehow, especially the PhD student, disappointed because if you compare here the first method, the computer vision method, and the pose regression by convolutional network, you see that clearly the average error is much bigger with pose inference by the deep network. However, it's bigger, but it's not that bigger. I mean, it's 2 times bigger, but it's still a few meters. It's still within the normal range of error of a GPS. And even in some cases, the computer vision was failing and the pose regression was not. So it has some robustness in the term of less fail case. But anyway, the main thing is that even if it's bigger errors, the computation, it was already noted by Kendall et al. In their papers, is much, much faster, because actually the bag of words matching and even more the translation, rotation, estimation by comparison of key points is very time consuming. So typically there is a huge factor between the two, so our system was not optimized at all, but we had like 75 milliseconds to infer the position from an image with the ConvNet, and 3 seconds with the geometric method. So it means that with the geometric method, if we don't optimize, it's just impossible in real time, or we can do it only every few seconds. With this, the position is obviously less accurate, but we can have it several times per second. So then, for the conclusion on this part, and then I will kind of open to propose you a bigger lesson about all the possibilities of deep learning for intelligent vehicles. But the lesson on this is that indeed it's possible to have localization purely from a query image, and even without having to patrol the same street before, because you can leverage the pre-existing panoramas of Google Street View or Baidu Street View or whatever. And you can hopefully get an average accuracy of the positioning around 3 meters, which is not bad. If you use deep learning, then Okay, the accuracy is lower, it's more 7 meters, but it's much more fast. And so it means that this approach can indeed be a fallback that can help to mitigate the GPS outage, or could work in tunnels or in the wire. As tunnels may be a bit tricky because maybe you have not enough differences along the tunnel, but maybe I was thinking more of underground parking, maybe, or this kind of thing. But you can have all other means. I mean, it's a general idea in intelligent vehicles that you would usually have several ways of computing the same thing for robustness. So for instance, normally you don't have only one sensor to analyze the surrounding. You have a camera, but normally you have also a radar, and normally you have also a LiDAR, except for Tesla, for some reason I never understood. But anyway, so I want to finish. I still have a few late, to give you a broader view, in fact, about all what can be done and what is currently researched with deep learning for intelligent vehicles. So you probably all know that it's very good and it's state of the art now for localizing and recognizing objects in real time, like all the cars, the pedestrians, even the traffic signs, traffic light, and so on. It can even do the full segmentation, where you will not only get the object, but also the road, the sidewalk, and all this. It is also very much used with specific versions like PointNet or the like, or VoxelNet, to do the semantic segmentation on LiDAR 3D points data. But what maybe you not all be aware of is that there was recently, 2 years ago, this breakthrough that even with any normal video, you can infer in nearly real time the skeleton of the people in the scene. So of course the interest for intelligent vehicle is not really this kind of crowd, because you wouldn't try to drive here, but it means that we can have more information on the pedestrians than just their trajectories. So for instance, I'm just beginning now a PhD student also with VDECOM to use this information for predicting whether or not a pedestrian is going to cross in front of the car. So it's really new stuff. And more generally, in fact, my message is that deep learning for intelligent vehicle can provide much more than just image analysis or semantic analysis of the image. So you have the estimation of human pose, but you have also echolocation, as I presented, but you can also now use it to infer an approximate depth image, even with mono vision. You can synthesize realistic images, and actually, that's what I'm more interested in, you can even try to use it for the planning and behavior part of the car. So this just to show you, this is not our work, and this is from UCL, also quite recent. So this is the input image and the infer approximate depth for the same scene. And what's very good in this case is that it's very easy to have the training set, because you can just drive many places with a stereo camera. You have the disparity, you estimate the depth on the stereo camera, and so you can have the input, which is one of the two cameras of the stereo pair, and the output, the depth estimated by disparity. So you can have loads of data and no need for human labeling, and then you can train and get this kind of results. So it allows with a simple camera to have much more than just the object. You can also have the approximate distance. Of course it's noisy, but it's better than nothing. And it can complement the LiDAR or the radar or whatever. So localization from vision with deep learning, I mentioned already. Here you have the original paper in ICCV, and also you can see that in their setup They had much better position accuracy, so we were a bit disappointed. But actually, the reason they had nearly a bit less than 1 meter, if you see their training set, it was a handheld camera and it was like moving a lot, so many intermediate images. So since we were restricting ourselves to using pre-existing panoramas, it's normal that we are lower. But they had somehow the same order of magnitude, like 2 times more precise with geometric method than with deep learning. And also here, probably their code was much more optimized than ours, but this kind of much faster inference of the neural network than the geometric method. So somehow it's reassuring that what we found on our experiment is in line with the result. And okay, so also a even more recent result that's will be very useful for intelligent vehicles. It's the possibility with a generative adversarial network to generate fake images so the idea is the input is this with colors, which is the exact semantic segmentation from the simulation software. And so from this as input, you can generate a really realistic looking video. And in fact, you can have the same semantic segmentation generating this or generating this, depending on how you change the parameter for the generation. So it's very, if you look in detail, it's like in the deepfakes, you would have some small problems. You can see that it's not a real video, but it's a good way to generate a lot of real-looking videos starting from simulation data, and so it means that you know the exact segmentation on all these fake videos. So you can do a lot of tests for this. So I think this will be very useful in the next year. Let's see. Okay, I have only 2 slides, I think. So just one example of the use of deep learning for not only looking around the vehicle, but for controlling the vehicle. So actually there was a paper by NVIDIA several years ago where they trained some end-to-end driving imitating human driver. So we kind of reproduced this result with Valeo, except that instead of having several cameras, they have one fisheye camera in front of the car, so it's easy to generate offsetted views. But the idea remains the same as in NVIDIA, is you have a convolutional neural network which takes one image as input and will put a driving wheel command or even a brake or accelerate. And so we trained this on 10,000 kilometers of driving recording where we have the actual action of the human driver in the situation. So the way it's done is we're trying to mimic a human driver, and if the data set is rich enough, we hope that what is learned has some generality. So actually it has, I don't have the video on this slide, but because we tested the stuff learned on the real image into a video game, like GTA I think, and it was working well, and it actually the Valeo even prepared a demo at CES in Las Vegas in 2018, showcasing that it's possible on their track. The vehicle was controlled both laterally but even longitudinal by a neural network. And for the lateral part, which I was involved in with my PhD student Marin, we have a paper in RelStat on this. And even more look ahead, and that's nearly the last, is, okay, trying to mimic a driver is good, but if we want to automate, it's because drivers are not so good. And also, if we try to learn only on existing really driven situations, you cannot have everything. Like you will not force to record when the pedestrian is jumping in front of you, for instance, because you don't want to roll over him. So we're convinced that we need to learn in simulation environments and that we want to be beyond just imitation of human drivers. So one type of machine learning method which is interesting for this is reinforcement learning. So we use it with a convolutional network taking the in-front image of the camera and putting the commands lateral on the driving wheel and accelerate braking. And what's interesting is that you don't need human labeling, because here, actually, in reinforcement learning, the algorithm is optimizing what is called a reward by just testing the agent in the simulation environment. So you just set the goals. So you say that, for instance, you want the vehicle to stay in its lane. So you have a negative reward which grows if you're not in the center of your lane. You put a target speed which goes to 0 if the traffic light is red, or if there is a car or pedestrian in front, and then you want the car to be as close as possible to the target speed. So by using just this and training, pretty long training, because in reinforcement learning it would need not 10, not 100, not 1,000 epochs, but really there had to be like hundreds of thousands of simulation of the agent every time improving itself. But in the end, the system was working pretty well, as you can see here, where it's actually stopping in front, if there's pedestrian in front. If the traffic light is red, it was on the other side. And what's good also in the simulation, you can modify the weather as you like and so on. And so we were very happy because my PhD student, funded by Valeo, it's an industrial PhD, won the first prize at the Kaola Autonomous Driving Challenge. So they have put a challenge for this where we were only provided the kind of learned autopilot, and they were testing in a city that we didn't have during training. So, I mean, the performance is obviously not perfect, but it was good enough to be the best performance compared to other vision-only guys in the simulation, in the competition. So that was just a complement to the very narrow echolocalization application I mentioned, is that we can do much more than just image analysis with deep learning, and in particular in intelligent vehicle, focus is now tending to look for planification, for reactive behavior, going beyond perception. Actually, it's a bit the same for intelligent robots also, because they're pretty similar. So, thank you. I can answer questions.
Okay, thank you very much. We have time for one question. So, yes, I see. At first, thank you very much for brilliant presentation. It's very interesting. But my question consists on a few small questions, short questions. The first of them, the system, as I understood, is learned before, preliminary learned system.
In echolocalization application, or?
Yes.
Yeah.
So it means that if will be renovation of any buildings, you know you need the update of this database.
This is a good question. I have to answer here anyway. I don't have the microphone. Yeah, it's a very good question. So actually, if there is a big structural change in the city between the panorama taken by Street View and your car running, you could be in trouble, it's true. What we've seen is that there is also the seasonal change, like you could have leaves on tree or no leaves on tree, or snow, or so we didn't investigate this too much. We think the seasonal change is not so much a problem. We think also the movable objects such as cars parked or this thing is not too much a problem either. But what's true is obviously if there is a big structural change here. So it means that if we do like that, we rely on how often Google scanning car is passing in your city to update. And actually, we had even in the idea in this PhD thesis, but we didn't have time to use this kind of approach to know that there should be an update. So it would not use it for ecolocalization, it would use it when you know your localization and you see that there is a discrepancy between the map and the image, and so you need to update somehow. So it could be another use of this kind of matching. You could have a threshold measuring the difference between the query and the actual image at this place, and say, okay, there is a big change, probably you need to update the panorama.
Thank you very much. Also, small question about resolution of camera. If you prepare and launch the system with the images of any quality, and then use the camera with lower resolution, the number of error will be increased.
We did not test that quantitatively either. In fact, the way we handle this is it's not only the question of resolution, it's also the focal length. So our way of dealing with that was that we tried to use, since the original panoramas, we need to rectify, so the generated, rectified images, we try to be as close as possible to the actual camera on the car for the focal length and the resolution. But obviously, if there's not enough detail in the panorama, you can have as resolution, but blurry, or so it's true that it can be a problem. But it's very high resolution, the street view in panorama and street views.
Okay, and last question, correct and short. If you use approximately, you said 10 frames, 10 images for one location, uptiming and learning. So by this you avoid from the image moving objects, cars, changed position, changed objects, and the area for recognition decreases on these places.
I'm not sure. When I said 10, actually I meant that
around.
Yeah, like the minimum is to have, because you don't know what will be the orientation of the car. Well, normally on the street it's supposed to be one way or the other, but it can be a bit offset. So it's more like that. So it's not that they are taken at different times, because usually there's only one panorama at a given time and at a given place in street view. But what we could do is, and we didn't have to do, is to generate more intermediate by taking into account two successive panoramas which may be taken at different times. And so we have this interesting idea that a car was in one panorama but not in the next one, and maybe it would help removing. In fact, there are many improvements possible. We could detect the moving objects like the cars and pedestrian on the image and try to remove them before computing the bag of words or before
and in new cities, it is a lot of typical buildings and typical crossroads.
Visual aliasing, it could be a problem.
Maybe
can use trajectory analysis.
The what?
Trajectory analysis. Previous localization for next.
What I would more believe is maybe vision only is not enough. For instance, in the ego-localization of the paper robot by Anne Baron, the PhD student, has discovered that vision only localization in corridors is just bound to fail because the corridor is the same all along, same on different floors and so on. So what he does is combining with a kind of Wi-Fi signature, like what are the Wi-Fi access points around. So maybe combining with some other information totally different from vision would be a better way to handle this visual aliasing, I think.
Okay, thank you very much, and sorry for this short question.
Okay, thank you.
Okay, in any case, thanks a lot for asking. You could continue your discussion during the lunch. Okay, so please don't run away. We have a gift for you. Thanks a lot for presentation. I believe it was a great overview, very useful for PhD students and master students where to dig one and where to find the problem to solve. So our plenary session seems over, but I have one notification for you that currently we are having lunch, so 1 hour, and you need to go to the second floor to the cafeteria, and as a participants of the conference you should present the following blue card, which is the current date and lunch. Yes, so this one should be presented to the staff of cafeteria, and you are allowed to take anything. Yes, so yes, I forget to tell that all the cards for today and for tomorrow are in badges, so try to find it. And I wish you a good time and Professor Grafowski, fruitful discussion during the lunch. Okay, see you during the sessions. Thanks a lot.